Hi, here we are discussing about a project hybrid protection of digital FIR filter. A digital FIR filter is a common building component in digital signal processing applications, and its behavior is defined by its coefficients. In order to hide filter coefficients from the attackers, the efficient avocations approaches has been proposed, either by hiding them behind decoys or by substituting them with a key bit. Okay, in this article we initially introduced a query attack that can discover the secret key of such a obfuscated FIR filter, which could not be broken by the existing prominent attack. Then we propose a first of the kind hybrid technique, including both hardware applications and logic locking, using the point functions for the protections of the parallel, direct and transposed form of the digital FIR filter. The experiment results shows the hybrid protection technique can lead to a FIR filter with a higher security while maintaining the hardware complexity competitive or superior to those locked by the prominent logic locking methods. To reduce the hardware complexity, this paper proposed approaches of the arithmetic operations with a XOR mux full adder design to reduce the number of logic gates in the FIR filter architectures. It is also shown that the product multiplier logic blocks and FIR filters are resilient to existing attacks. Okay, so this results on different form and the realizations of the FIR filter shows that the parallel direct form FIR filters has a promising potential for secret design. This work we have developed in Verilog HDLs and synthesized in Xilinx Vertex 5 FPGA. Okay, now we can verify the paper. So this paper mainly focused for the digital FIR filter. So digital FIR filters means we need to concentrate on the coefficients, okay, and the filter order. Okay, so filter order means one adder, one multiplier and one delay is called a filter order, and this coefficients means it will decide the filter. It's a low pass filter, high pass filter, band pass filter, band stop filters. Okay, so depends upon the coefficient we can decide it. Okay, so based upon this coefficients we need to mask from the attackers. Okay, and to protect the filter coefficients from the adversary, efficient application technique in the proposed architectures. Okay, so here we have used three different architectures. Okay, so if FIR filter means we know the architecture, the basic simple architecture. So that is a figure 1. Okay, so design of a FIR filter, that is a parallel direct form. Okay, the figure A, and figure B is a parallel transposed form. Okay, and figure C is a folded transposed form. Okay, so these three different architectures will be handled here. Okay, so here the C0, C1, C2 up to Cn minus 1, it's called as a coefficient, and x of j as a input and y of j is a filter output. Okay, so folded transpose form. Okay, so here we need to put the coefficients value in the multiplexers, not directly to the multiplier. Okay, so multiplexers selection point will decide so which coefficients we need to multiply it and which time. Okay, so everything, this counter block will be decided. Okay, so here the proposed architectures of this multiplications part. Multiplications part means coefficients based multiplications. Okay, so here they are given some examples. Okay, so realizations of CAVM and MCM and DMCM. Okay, so MCM means it's a multiple constant multiplier. Okay, so the architectures of CAVM and MCM and T transpose multiple constant multiplier was designed. Okay, so here this is the examples of the coefficient designs. Okay, so here the 57 and 81 is a filter coefficient. Okay, so here we need to add the form using x1 and x2. Okay, so x1 into 57 and x2 into 81 means we will get x1 57 and x2 81. Okay, well, plus okay. And this is a form, okay, for the proposed architectures, okay, without multiplier configuration. That means a multiplier less configuration, okay. So here so this is a MCM model and this is a transpose model. So here if we get any coefficients from the MATLAB, okay, we need to develop the new architectures. We can't use this architectures in our development, okay. Why? Because this is an example design, okay. All the designs come up with 57 and 81 only. So here for this development we have used a MATLAB GUI, okay, filter design analysis tool, okay. So we have generated a coefficient for low pass filter, FS, sampling frequency equal to 50 MHz and cutoff frequency equal to 5 MHz, okay. So this is a filter coefficient generations model. So this is a coefficient, and this coefficients we have converted into the binary form, and after that it will be converted into the decimal form, okay. So here 1 6 21 35 35 21 6 1, okay. So this is a form, okay. So as per that we need to create a multiplier with 3 different architectures: CA, VM, MCM and TMCM, okay. So here example, this direct form multiplier means how we can develop the equation, okay. So example, I will draw one equation, okay. So here I will draw 1 x1 plus 6 x2, okay. So how we can give means x2, okay, shifting 1 and shifting 2, we need to add this, okay, and again x1 so here 1 dot x1 plus 6 dot x2. So this is a form. So how these architectures we have created means so this is x2, so input you can give a 1, okay. So 1 means you can assume it as a binary 0 0 0 0 and 0 0 0 1, okay. You need to shift the bit into 1 times, okay. 0 0 0 0 0 0 1 0 and shift the bit into 2 times, okay. 0 0 0 0, okay, 0 1 0 0, okay. So this is called 4 and this is called 2, okay. So 4 plus 2 equal to 6, okay. So this is a simple technique. So as per the technique we need to develop the architecture using this paper, okay. So with all the coefficients, okay. So then only we can come up with the proposed architecture, okay. So here, so this is a proposed architectures, okay. So the CAVM architecture, okay, figure 7, the relations of applications of CAVM block including content 5781, okay. So example design architectures they are given, okay. So A is a straightforward and B is a CAVM mult, okay, and C is a CAVM SA, okay, and this is a MCM architecture, okay. So relations of applications, and this is a proposed architecture of the MCM, okay. So here TMCM architectures they are not given in the paper, but in the comparisons of multiplier and also for the locked multiplier blocks, okay. So here the table 4, okay. So this is a final locked FIR filter comparisons, okay. So here they are compared, the direct form means it will come with 3 comparisons, okay. CAVM M mult, okay, and CAVM SA and CAVM CRK, and transpose form, folded form, okay. Totally 9 comparisons was given here, okay. So we have developed all these comparisons with the proposed architectures using a XOR mux full array design, okay. And so this is a comparisons of the folder coding design. Okay, so direct form, this 3 is a direct form, and this 3 is a TCM folded form, and this is 3 is a transposed FIR filter form. Okay, so we have developed all the multiplier architectures with the novelty. After that, we have developed a FIR filter design. Okay, so here we can verify the one by one architecture. Okay, so here, so this is a simulation output for direct FIR filter CAVM method. Okay, so filter input and filter output. Okay, so here input we have given 2 MHz input frequency we are given here. Okay, and the simulation output almost same for all the FIR filters, so it not be changed. Okay, but the comparisons part of the logic sizes of area, delay and power, it may be changed. Okay, so here we can check any architectures. The first initially start with this one is a direct CAVM mult. Okay, so direct FIR filter CAVM mult. Okay, so here you can verify that. So you can analyze the number of slice registers, number of LUTs and number of occupied slices, IO base. Okay, and you can analyze the RTL schematic. Okay, so this is a direct form architecture. So CAVM, 2 CAVM mult we have used in the architecture. Okay, so here direct form means in the figure A1, the parallel direct form we need to use. Okay, so first the X of input we need to delay it. Okay, then we need to give the delayed input to the multiplier. Okay, so in the multipliers we need to use the coefficients and some other architecture. That means as per the proposed architectures we need to develop the CAVM architectures, right? That architectures we have used it here, and finally come up with the Y of j. Okay, the same method we have used it here. Okay, so initially the input was given into the flip-flops. Okay, so each flip-flops will be shifted. Every sampling values given to the CAVM multiplier. The 2 multipliers we have used here. Okay, so inside of this CAVM we have used a CAVM single bit architecture. That means 1 plus 6x. Okay, so that architectures was here. Okay, and the multiplier part of this architecture FIR filter, we have used a array multiplier, 8x8 array multiplier, and addition part we have used a ripple carrier adder with the XOR mux full adder configuration. Okay, so here this is a multiplier configuration. Okay, so here we have multiplied it and finally come up with the final addition. Okay, and the final addition of to the 2 multipliers we have taken. Okay, and it will be given into the final adder. Okay, so this one. Okay, so this is a CAVM direct form. Okay, multiplier. Okay, and transpose form means we can check here. So here also you can analyze the FIR filters, slice registers, LUTs and occupied slices, everything. Okay, so this is a transpose form MUL. Okay, so this is a transpose form. So transpose form means once we are multiplied the value, then we'll start with the addition and delayed. Okay, wow. So this is the transpose of the MCM block. Okay, so here the filter input directly given to the 2 multiplier, we are not created any delay. Okay, so the internal architecture of this block we have started with the multiplication. Okay, so here MCM also this one is a multiplier-less architecture, and this 2 multiplier we have used. Okay, so directly the input given to the multiplier. Okay, so the multiplier output will start with the addition. After that we created a delay, and after that final additions will occur. Okay, the final addition output again with the 2 MCM multi architecture addition occur. Okay, then we are taken as a output. Okay, so this is a transposed form. Okay, and folded form, you can check anything, CRK or MUL or SA architecture. Okay, so this is a running procedure. Okay, so this is a folded form. So folded form means this method. So this method, so it will support with the counter blocker. Okay, so counter blocker, so this one is a counter blocker and this one is a multiplexer. Okay, so array multiplier, RCA. Okay, so this is a number of D flip-flops. The final output of the D flip-flop we are taken as a output. Okay, so actually all the architectures will come up with a different RTL schematics. Okay, so here totally 9 items was we have developed it. Okay, and this all the things we have simulated in modelism and synthesized in Xilinx vertex 5 FPGA. Okay, and we have taken all the parameters and that parameter output given in a document. Okay, so this is a document. Okay, so this is a comparisons analysis of number of slice registers, LUTs, occupied slices and IO base. Okay, and delay and power. Okay, so here the power is almost same. Okay, 526 and 527. Why? Because the number of slice registers, the percentage. Okay, so utilization percentage almost it will take 1 or 2% only. Okay, compared to the available. So that's why this 1%, this minimum level of power will occupied. Okay, and other than that the area and delay it will be vary. Okay, and we have written abstract document for this project. Here this is the base paper abstract, improvement of the project, proposed title, proposed abstract, existing system. Okay, disadvantages, proposed systems, advantages. Okay, and related notes. Okay, finally come up with the literature survey and references. Okay, thank you.